Okay, yep, sorry. Okay, so chapter 7 is about the moving beyond linearity. So the first we think about just the situation that we have the one x and one y. So x and y here. So we have the some plots, and the relationship between x and y is more complicated than just straight line. So if we fit the straight line, maybe then we can draw this line, but this is not the optimal line. So probably we want to fit more complicated curve like this. So how to do that? And we have the many methods. Yeah, so so these slides are not many, but we have many applications. So the lab session have at least 16 pages. Yeah, so the most basic model to relate variable x and y is this linear model, but we have many ways to go beyond the relationship. And the one important thing is that when we say linear model, so this is original definition of linear model. So we have two meanings. One is this is a linear function of x. And the other meaning is this is linear with respect to beta 1 and beta naught. And in statistics, our interest is how to determine beta naught and beta 1. So as long as the model is linear with respect to parameters, that we can fit the regression in the same way as the simplest case. So this the polynomial regression that works just in the same way as linear regression. So we have basically the variable 1 up to variable d. So actually the xi is x sub I is x to the i's power, but basically this model is the same as a linear regression model with d variables. Yeah, so we can describe this kind of the complicated relationship by, for example, the quadratic regression model. So this should be useful to estimate the some x which maximize or minimize the y value. Yeah. So the President Reagan, I think his advisor suggested to lower the tax rate to increase the tax revenue because we have some optimal point to correct the maximum amount of tax. If tax rate is too high, then economy shrinks, and also many people try to escape from tax. So in some cases, if we lower the tax rate, then we can get the larger tax revenue. So x is the tax rate and y is the tax revenue. So it depends on the case, and that wasn't successful at the time, but theoretically we can do that kind of analysis. For example, also I saw an analysis on what is the best percentage to maximize the tax revenue for tobacco cigarettes. So if the tax rate is too high, the sales goes down, or maybe the cigarettes are traded in the underground market. But if tax rate is too low, of course, tax revenue is low. So we have some point to maximize some number. So statistically, the polynomial regression that works good. I mean, quadratic regression model that works good. Actually, it's hard to find this kind of example. Usually because of the error of the regression model. So this is one example. So this is the age and wage of the people, and the wage is maximized around the 45 or 50. And if we fit some fourth degree polynomial, then probably we can identify what x value, what age that gives the maximum wage on average. Sorry, this is the polynomial regression, and Yeah, I think that you can ignore this for now. So this is basically the fitting the probability of getting a higher wage more than 250,000. Yeah, so logistic regression case. So in logistic regression also the explanatory variable, the predictor variables can be multiple. Can be polynomial, but yeah. So maybe the for now that we can just think about this the regression case. And another example that we had is the step functions. So this is also a very flexible approach. So if we pick some knots, so then we fit some the flat function, the constant function for each the interval, then we can fit pretty flexible the curve, not curve, but the pretty flexible the step functions. So here, basically, we prepare the several functions. We have the k+1 functions, which are just the indicator function of the mutually exclusive intervals. Then we determine that these constants. So these are level. So here, then this is the beta naught, maybe here. So beta naught, and here is beta 1, maybe beta 1 hat and beta 2 1 hat, and here is beta 2 hat. Okay, so if we estimate beta naught hat, beta 1 hat, and beta 2 hat, then this is a pretty flexible model, even though this isn't a smooth curve. Yeah, but usually the most difficult thing is how to choose C1 to CK. So you can see that this equation is linear in terms of beta naught to beta k. So once we fixed the C1 to CK, then it's easy to estimate beta naught to beta k. But how to choose C1 to CK, that isn't really trivial problem. And basically, we have to try infinitely many cases. Now, in fact, that we don't have infinitely many data points, so maybe we can. If we have n points, then we only have n-1 possible knots, but still we have too many. So we have some technical difficulty to fit the model. But once you decided the optimal knot points, probably around here and here, then we can fit the model. So also another problem is how many knots we should have. So that is another issue. So that's also difficult to solve. Yeah, so you can imagine that this problem is probably very complicated, right? So that we have some restrictions such as C1 is smaller than C2. Otherwise, we cannot identify. If we switch C1 and C2, then basically the result is the same. If we have 3 points, we have 6 combinations to order C1, C2, C3. So we can see that that kind of problem is more complicated. Yeah. Yeah, so this is basically the 3-piece. So the k is equal to 2 knots, and this is 3 knots. So not point is this 3. Yeah. Yes. Okay, so do you have any questions so far? Okay, so now that we go to the next section, I think this is the new section. So basis functions. So basically, we generalize the idea of the step functions. And we now have functions b1 to bk. So this may be polynomial, for example, x to the kth, bi, maybe the x to the ith power, or just arbitrary function. For example, the b1x is, for example, sine of x. And maybe b2 of x is sine of 2x. And bkx is the sine of kx. Then we have kind of the Fourier series. So we can approximate the curve by, the overlaid the sine curves. So this is one case. So then, we can see that this curve is the pretty smooth. We can differentiate the function as many as you want. And also it does not blow up. So if we think about the summation of the sine of ix, then if x goes to infinity or negative infinity, there's still it's just the periodic function, so that it does not blow up, unlike the polynomial. So this is one good example, but just to generalize the step function into k different functions. So this is basis functions. So you can choose any b1 to bk. It's pretty arbitrary. But anyway, so we estimate beta naught to beta k, so we can find some function. Yeah, so the polynomial and the so polynomial and sine curves. So these are probably the most common examples. Other examples, so we will see the spline, but those are probably the most important applications. So next, we think about a special case of this basis function. So just we think about the two bases. Not two bases, sorry. This is slightly different. Sorry. Okay, so now that we want to extend the polynomial regression. So so polynomial regression. So the polynomial regression, for example, the degree 3, the yi is a function of the xi and linear combination of xi and xi square and xi cube. But here that we make one knot point, and we think about the piecewise, the polynomial functions. So this is the piecewise cubic function. So suppose we have x here and y here, and suppose we have some functions like this. Then you can see that if we have the one knot, maybe here is C, then we can fit the curve, the cubic curve for these two pieces, maybe this cubic function and this cubic function. So each piece is cubic, but this piece and this piece are different cubic functions. So say that we have, so this part, so this part is equal to f1 of x, maybe xi, and this is f2 of xi. Then, so this is the y is equal to f1 of x, and this is y is equal to f2 of x. Then at least it's more flexible than polynomial regression. Right? So, and it does not blow up too quickly. So if we think about the 6th-degree polynomial, then so maybe 7th-degree polynomial. So we have the 8 parameters here, right? So we have 8 parameters here. So alternatively, we can set up the 7th-degree polynomial, such as beta naught plus beta 1 xi plus beta 2 xi square plus beta 7 xi to the 7th power. So this has the same flexibility as this model, but probably the model is better than the second one, because if we use the 7th-degree polynomial, it blows up pretty fast. If you plug in xi is equal to 10, so that becomes the 10 million. So xi to the 7th power becomes 10 million. So usually it's problematic to fit the higher degree polynomial. So, but this case, the piecewise polynomial, we have only xi to the 3rd power. So still it blows up if x gets larger, but the situation is much better than 7th degree polynomial. Yeah, but this is a little bit ad hoc. So for example, this yeah, so this graph does not look too bad, but if we think about the more complicated data, sometimes this method is the too ad hoc, because suppose that we have y and x here, and suppose we have the like this, then okay, so we prepare a knot point, then maybe the fitted curve looks like this. Okay, so sometimes these two curve is not continuous, so totally different the curve, and it's discontinuous at C. And this is very unlikely graph. For example, if x is the time and y is some measurement such as temperature, then temperature does not jump from one point to another point. So this model is not likely, even though it fits the model. It fits the data in some way. So we want to impose some condition. For example, at point C, so this point and this point are the same. So the function is continuous. And even continuous, if it's not smooth, it's very unusual. So usually, for example, if x is the time and y is the position, then the position changes smoothly. So we want to expect the derivative at this point. This derivative from the left and the derivative from the right should be the same. So we want to impose those conditions to make a smooth curve even when we have piecewise polynomial function. So that is the idea of regression spline. Yeah. Yeah, so regression spline is the piecewise, the cubic function. So usually cubic. So we can think about the the piecewise linear function or piecewise fifth degree function, but often we use the piecewise cubic function. And has k knots. The k is typically a small number compared to the sample size. And we impose the function is continuous and the same first and second derivative at knot points. So yeah, so that is called the cubic spline. So that is denoted by this way. So you can see that the B1 is the part for function for all x in real numbers, and the B2 is the function for x is larger than C1, and the B3 is function for x is larger than C2, and the final bk plus 3 is for, yeah, so ck is x is larger than ck. So like this. So sorry, maybe this is not really sorry, maybe sorry, a little bit different. Sorry. What should I say? Yeah. Yeah. So sorry. So yeah. Yeah. So yeah. So sorry. So this is the piecewise cubic function. So basically, we should have the beta naught plus the beta 1 x, maybe xi, plus the beta 2 xi square plus beta 3 the xi cube, right? And yeah, yeah, I think we cannot explain it in one step, so that I will do one by one. But okay, so the fact is that the if we have k knots, so we have the k plus 1 components, and each part is cubic, and we have this condition, continuous and first and second derivatives are the same, then basically we need the k plus 3 parameters. And the reason is that if we have, okay, so knots such as C1, C2, C3, and that we think about the curve, then we have basically the 3 degree, we need 3 degrees of freedom for the first piece. Okay, so this is the beta naught plus beta 1x plus beta 2x square plus beta 3x cubed. So we need the 3 degrees of freedom, okay, 3 parameters. Then C1 to C2, we have another cubic curve such as this. Okay. So cubic curve that again have 4 parameters. Okay, so sorry, if we include beta naught, we have 4 parameters. Okay. C1 to C2, we also have the 4 parameters, but we have 3 constraints. So one is continuous, and one is first derivative, and the other is second derivative. Okay. So that means actually that we only have the 1 degrees of freedom. So to make it the continuous and the first and the second derivative coincide with the first part, we lose 3 degrees of freedom. So we only have 1 additional degrees of freedom. And we continue the same thing for C1 to C2. So we have again the 1 degrees of freedom. Then finally, we have the 1 degrees of freedom, 1 degree of freedom. So finally we have the 4 plus k parameters. Here k is equal to 3, but basically 4 plus 3 parameters we need to describe this function. So that means that except for intercept, we have the k plus 3 parameters. So basically, the regression spline is special case of the linear basis function with k plus 3 functions. Yeah. So this is the more concrete description of this. So oh, sorry, go ahead.
Sorry, Professor.
Yep.
For cubic function, we have k plus 3 or k plus 4 parameter.
K plus 4 parameters. So k plus 3 basis function plus intercept.
Okay, thanks.
Yep. Yeah, so this is the more concrete description of the regression spline. So at first, the cubic function has the 3 terms in addition to intercept. Okay, so this is the most left-hand side in the previous figure. Then after passing each knot, the xi, each knot xi, xi is one of c sub I, the following basis function is needed. So that is actually the positive part of the x minus, x minus the xi, the cube. If x is larger than xi, and this is 0 if the x is less than or equal to xi. Okay. So this is because, think about this graph. And okay, so think about the first piece. First piece is cubic function. And suppose this cubic function continues like this. Okay, then what's the difference between this original cubic function and the second piece? What's the difference? So difference should be 0 at x is equal to c1. Otherwise, it is not continuous. And also, if this is c1, actually this difference, so this difference, what's that? So suppose this difference is what the h, sorry, the h x c1. So hxc1 is okay. So at first the no intercept, and also the if we write this as x minus c times maybe beta maybe gamma 1 plus gamma 2 x minus c square plus gamma cube times x minus c cube, then this part gamma 1 should be also 0. Otherwise, at c1 we have the different derivative from the left hand side and right hand side. So this should be 0 to make the derivative equal to 0. Derivative the same. So derivative exists at c1. So derivatives from the left hand side and right hand side coincide. And also to make the second derivative coincides at the x is equal to c1, the gamma 2 should be 0. So if you differentiate this function twice, then basically that should be 0 at c1. And if you differentiate twice, then just the gamma 2 remains, right? So x minus c disappears. And here, if you differentiate twice, still we have x minus c. So if you plug in c is c1 here, and then that should be 0. So that means the gamma 2 should be 0. So gamma 1 and the gamma 2 should be 0. So the intercept, of course, 0. So we only have the last term. So only this term remains. So that means the difference between the first curve, so this orange curve, and the second portion, so this the green portion. So difference between the orange and green should be this shape. So gamma 3 times x minus c cube. Yeah, so that's why after that we have the intercept and x square and x cube, that we should have this function for each ci. So that makes the the k plus 3 the basis functions. Okay, so x and the x square and x cube and the h of xc1 up to h of xck. So this is k plus 3 basis functions. And plus intercept. So that we have the k plus 4 parameters. So that is the linear, regression spline. So it's the same as the fitting the linear basis function with the k plus 3, the specific basis. Yeah, so this illustrates the situation of the spline. So cubic spline with one knot. Knot is the dotted line is here. Okay, so this is cubic curve. And this is also cubic curve. But it's continuous and the same derivative at this point and the same second derivative at this point. So how many parameters for this one? How many parameters? How many parameters on the left-hand side, this side? This is cubic function, so how many parameters? Beta naught plus, beta 1x, beta 2x square, and beta 3x cube. So the 4 parameters here. And how many additional parameters here? Anyone?
One, we have one additional.
Yes, you're right. So this is cubic function, but so we have 4 parameters, but we have 3 conditions: continuous, the same first derivative, and the same second derivative at this point. So we have to subtract 3. So we have 1 parameter. So in total, we have 5 parameters. And other cases are these here and here and here. So piecewise cubic function. So we don't have any restriction. It's even not continuous. And you can see the derivative is also different. Okay. And second derivative, we cannot really see in the graph, but probably it's not the same. So we have how many parameters here? So model assumption isn't really described, but you can see just independently the two cubic function.
4.
Yeah, 4. 4 plus 4, right? So we have 8 parameters here. So this really depends on how you specify the model. But this model is a little, ad hoc and not natural. Right? So of course, this is more flexible because we have more parameters, but probably that you want to have this kind of more smooth function. And some other cases, the continuous piecewise cubic. So this means that we have 4 parameters here, cubic function. And this is cubic, but we have continuous function. So we have, we lose the 1 degrees of freedom. So basically, this is cubic function plus x minus, if we have c here, x minus c, maybe gamma 1 plus gamma 2 times x minus c square plus gamma 3 times x minus c cube. Okay, so we have the 3 parameters. So just continuity, no restriction on first derivative and second derivative. You can see this function is not differentiable at this point. Okay. So we have 7 parameters. Yeah. And another thing, and another thing is the linear spline. So originally this is the straight line. So this is linear. So we have how many parameters on the left-hand side? Linear.
2.
2. Then this part is also linear, but we restrict the value at the 50. So this is continuous. So we lose 1 degree of freedom, 1 degree of freedom. So the 2 minus 1. So this is 1. So in total, 3 parameters. So this is called linear spline. So the previous one we discussed is called cubic spline because the piecewise component is cubic. But here that we say a linear spline. So basic idea is that for cubic spline, even though we have 4 additional parameters, that we impose the 3 more the restrictions, so that actually we only have 1 additional parameter. So the structure is same here. So linear regression. So we have 2 parameters for each piece, but that we make 1 restriction. So we only have 1 additional parameter for each component. Yeah. So it's possible that to think about the cubic, maybe quadratic spline, for example, each component is quadratic. So we have 3 parameters, and we have 1 additional parameter for each additional interval. Okay. So then we can restrict the the continuity and the first derivative. But that is a little bit unnatural because I don't know, but usually each piece is short, each interval is short. So usually simply that we have some slope between some knot point to next knot point. And if we use the quadratic function to represent trend, it sounds a little strange. Right? So quadratic function is symmetric function, the parabola. So usually when we want to approximate this curve, usually we use just a straight line or maybe a cubic curve, but usually we don't use the quadratic equation. So that's why probably it's not so popular. But yeah, theoretically we can think about it. But maybe linear spline and cubic spline. Cubic spline is the most common regression spline. Questions? So one question. So how to determine knot points? So it's pretty complicated. Right. So if you think about the writing code, that you can immediately see the problem. So gamma 1, gamma 2, gamma 3, so these parameters, it's not difficult to estimate. Anyway, this is a linear basis function. So we can just use the theory of linear regression. We can write the regression model as this shape, y is equal to x beta. Then the beta hat is equal to x transposed x inverse x transposed y. So we can immediately get the coefficients. But the knot point is really complicated, right? So this changes the basically the predictor itself, right? So the one column of x is the so the certain columns of x includes the threshold information. So that part, if we change that threshold, then entire matrix X changes. So how to optimize that number, the threshold? So that isn't very easy. So because of this reason, the regression spline isn't really convenient. So the first time I used regression spline is to fit the yield curve. And yeah, so you can see the interest rate depends on the maturity. So this is maturity. And this is the annual interest rate yield. Then usually interest rate is low for shorter maturity, 1 or 2. But the interest rate gets higher towards maybe 10 years. After that, pretty flat or something like that. So this is a complicated curve. So, but the market people have some intuition on what are the important points, such as maybe the x is equal to 2 and maybe equal to 7 and 10 or something like that. So then I can fit the cubic spline. Yeah, but unless we are not sure about how to determine the knot points, it's really hard to fit this model. Yeah, so it's difficult to fit the knot, to decide the knot points, and also how many knot points we want. So it really depends. So for example, the bond market, that is somewhat clear because they have some futures, the bond futures. So the futures determine the overall shape. So basically, no one is interested in the 6-year treasury yield, but the more people are interested in 5-year yields or 10-year yields. So if we use that kind of information, then we can, set the knot points maybe between 5 and 10 or something like that, in between 5 and 10 or something like that. But usually it's hard to choose knot points. So then this is another way to determine the regression, the spline function. So that is, okay, so just minimize this function. Just minimize this function, but we impose some restriction on the smoothness of curve. So basically, the second derivative represents the smoothness. Yeah. So if we have maybe for discrete case, second derivative gets larger when the graph is like this. If G prime prime is small, that means the graph does not change dramatically. Right, so you can see that discretized case. So this is time point 1, this is time point 2, and this is time point 3, or so on. Then you can see that we have large decrease and then the large increase. Then the second difference gets larger, right? So second G prime prime is the second difference in the discretized case. So that is the difference between this increase and this decrease. So maybe if this is 10 and this is 2 and this is 11, then basically this is 9 minus 8, so 17. So second derivative gets larger if the transition is not smooth. So that means that if we penalize the second derivative and over all the numbers, I think for the real case that we only restrict this in certain interval. But so this is the second difference. Second difference. If we think about the second derivative, if we penalize the second derivative, I mean the absolute size of the second derivative, we restrict that one, then we can get the smooth curve. So if we have large lambda, the smoother curve, and if small lambda, we don't penalize the larger fluctuation of g of t, so that we have the more complicated curve. So lambda is large, then smooth. So lambda is small, g is not smooth but more flexible. So we have to determine lambda later by cross-validation, but we just use the arbitrary, the g of xi. So usually we use the cubic spline with the as many as knots possible. So if we have n observations, then we use n minus 1 knots. So of course, if we have n observations, it does not make sense to have more than sorry, if we have n observations, it does not make sense to have more than n minus 1 knots, right? Because the midpoint of the two neighboring observations, we only have the n minus 1 midpoints. So n minus 1 knots. Then okay, so we use the most flexible model, but we impose this assumption, this restriction, this penalty, so that the g does not become too complicated. Yeah. Yeah, and the degrees of freedom. So if we used polynomial regression that we have, if we have yeah, so that we can calculate the degrees of freedom of the model, right? So that if we have the k parameters, degrees of freedom is 1, degrees of freedom is k, right? So that we can describe the flexibility by the number of parameters. But here that we cannot. We basically have so many parameters, n minus 1 knots. So that means that we have the 3 plus n minus 1 parameters, right? So the n minus 4 parameters, n plus 2 parameters, sorry, n plus 2 parameters. But we have this penalty term to determine g. So we cannot use the number of parameters to represent the flexibility of the model. So how to determine the degrees of freedom? So that is the number of parameters in the model. And we have similar quantity to df for this case. So how to determine it? So that is by this case. So yeah, so we think about the fitted value y hat as the linear combination of x1 to xn. So remember that we have observations. So we have observations x1, y1 to xn, yn. Okay. So that means we can solve the linear system of yi is equal to summation beta ij times xj. J is equal to 1 to n. Yeah. If we have the duplicated xi's, then maybe the situation is slightly different. But suppose x1 to xn are distinct, then we can solve this equality because we have basically n equations. There's n equations and n equations. Sorry, I think this is a little redundant, the specification, but we have n parameters. Yeah, sorry, we only have the basically n parameters. We only have n parameters. So yeah, we use the n-1 knots. So okay, so the detail is not clear, but basically that we have about the n variables and we have the n observations. So we can solve the equation of the yi is equal to the summation of beta I jxj, and that we have j is equal to 1 to n. Yeah. Sorry, that it's not 100% clear, but basically we have we need up to n parameters to represent this function. Right? So we need only up to n parameters to represent this function. So we can solve this and to determine the beta ij. Then once we determine beta I, oh sorry, why? Sorry. No. Sorry. Sorry. Just a moment. So okay. So suppose we have x1, y1 to the xn, yn. Then we estimated yi hat to yn hat by the basis. The spline, the smoothing spline. So we get the y1 hat to yn hat first, right? Then we have the y1 to yn. Those are actual observations. Then we can solve the equation. The yi hat is equal to summation of beta ij times the yj hat, yj, observation yj. And j is equal to 1 to n, okay? Then we can solve the system of linear equations. Then we can determine beta ij. Then we say that beta ij as S lambda. Okay. So it depends on lambda, but okay, so lambda is somewhat fixed, and determine lambda, then we can estimate this S lambda. So S lambda is equal to beta ij. So matrix of beta ij. Then the sum of diagonal parts of S lambda is called the effective degrees of freedom. Yes, so S lambda is n by n matrix. Yeah, so df lambda is defined by the sum of the diagonal term. So okay, so it's a little bit more complicated, the definition, but we think about just the two examples to see what's happening. So what is the most flexible model? most flexible model that we defined, yi hat is equal to yi. Okay, so just it fits the data. So this is the situation that we just connect all observations to determine the g of x. So we have x1 here, x2 here, x3 here, x4 here, x5 here, and so on. The most flexible model is just connect these points. G of, if lambda is 0, then basically we get this. Okay. And for this case, actually the S lambda is equal to, so I think the S0. So lambda is small, then we don't penalize it at all. So S naught is actually this identity matrix, right? So because yi hat is yi for all i's, so that means the y hat is a vector of yi hat is equal to y. So that is the identity matrix of n degree times y. So S0 is equal to the identity matrix is the n degrees of, so the n by n identity matrix. So that means the diagonal terms are all 1. So that means the degrees of freedom is n. df0 is n. Okay, so this is consistent with our definition. So yi hat is equal to yi. So that means that we prepare one parameter for one observation. And we have n observations, so we have n parameters. And it's consistent that the effective degrees of freedom, the df0 is equal to n. Okay, so at least we confirm that it's consistent with the definition of degrees of freedom if the model is most flexible. Okay, so we think about the other extreme case. So yi hat is equal to y bar. So this is the simplest model. So just we take the average of yi's, then just we make it an estimate for all yi hat, all yi's. So in this case, what's happening here? So basically, we take average. So that means the 1 over n times summation of yi's. So in this case, the s, I would say s infinity. So we penalize the smoothness at maximum. Then, so y bar, so average of y is just the 1 over n times y1 plus 1 over n times y2 up to 1 over n times yn. Right? So that means everything is 1 over n. So that means the diagonal term, if we take summation, so this is n by n matrix, so the summation is 1. Okay. So that means so df infinity is equal to 1 over n plus 1 over n plus 1 over n. We have n terms, so this is equal to 1. So this is again consistent with the definition of degrees of freedom because we only have one parameter, right? So the yi is equal to basically beta naught plus epsilon. So this is the model, right? So then beta naught hat becomes y bar. So we only have one parameter, and it's consistent with this definition. So df infinity, effective degrees of freedom, becomes 1. So this is consistent with this estimate corresponds to this model with one parameter. So yeah, so if we describe it a little more, so to determine yi hat, to determine yi hat, if we use the large portion of yi, so we put the large weight for yi, then that means the model is more flexible. Right? Because to describe yi hat, we use the information of yi, so it fits to the data more. So yeah, so that means that diagonal term is large, then basically model is more flexible, so more data oriented, so but more complicated. Okay. So it sounds that this is a kind of reasonable definition of degrees of freedom for this smoothing spline. It does not guarantee it's exactly the same for the all cases, but it sounds the very reasonable definition. Yeah. Do you have any questions? Yeah, so smoothing spline is much more convenient than regression spline because we don't have to define the knot points. So just to fit the data, then okay, lambda is automatically adjusted in some way, the cross validation, then we can use it. So everything is more automatic, so it's more convenient. Okay, so this is how to optimize lambda. So to optimize this kind of hyperparameter, that we use cross validation. But for this the smoothing spline, usually we use the leave one out cross validation. So we have, for example, the twofold cross validation, tenfold cross validation. But what's the benefit of leave one out cross validation? That is, okay, so we use the maximum amount of data to train the data, to train the model. If we have 100 observations, we use 99 observations to train the model. So that is almost mimic to use the all observations. So that is one benefit. And also this method does not have any randomness. Okay, so we use the all leave one out cases. So we exclude the first observation, or we exclude the second observation. We try all 100 ways to exclude one observations and take average, take the sum of all residuals. So we don't have any randomness. And only the drawback is that it takes so much time. If n is 10,000, we have to run the model 10,000 times. But for this smoothing spline, we have convenient algebraic formula here. So once you fit the model once, just once for all observations, then we can calculate this quantity. Okay, so yi is existing observation, and the g hat lambda xi. So this is the estimated by all observations. So we only have to fit the model once. Then S lambda is obtained by solving the linear equations. Yi hat is equal to summation of beta ij yj. So we only have to do once. Then we can calculate the entire quantity once. So because of this formula, leave one out cross validation is fast enough. So we don't have any, the cons to run leave one out cross validation. So usually that's why we use this LOCV to optimize lambda. So this is the smoothing spline for the previous data, age versus wage. I think in the last figure, the previous figure, that we used the quadratic function, the polynomial with degree 4. But here we optimize that degrees of freedom. And it compares with actually the cubic spline with 16 degrees of freedom. I don't know the knot points, but maybe this is also smoothing spline. Sorry, the smoothing spline with 16 degrees of freedom, and this is the smoothing spline with 6.8 degrees of freedom. This is optimal because it's chosen by LOCV. Okay, so you can see that the red line fluctuate around this blue trend line, and it does not sound to have much information than blue curve. Red curve does not have much more information than blue curve. Just it fluctuates more. So probably the blue curve is better.
Sorry, Professor. How can we have 6.8 degree of freedom.
Yeah, oh, that's a good question. So okay, so the smoothing spline, So at first we optimize lambda. Okay, so lambda by this the LOCV, and once you estimate lambda, then you can calculate the S lambda. Right.
Okay, but I think that's I thought that degree of freedom, it can just be integer number.
Oh, yeah, so the degrees of freedom. So the degrees of freedom is the effective degrees of freedom. So this is defined by the summation of the diagonal term of S lambda sub S lambda. Okay, so for actually this example, actually this is the integer, but in general, it's not an integer. For example, we think about so simplest case, the y1 and y2. Y1 is the 1/3, sorry. So this is typical situation. So if we solve the linear equation, maybe y1 is the 2/3 times y1, sorry, the other way around, sorry. Y1 hat is the 2/3 times y1 plus 1/3 times y2, but the y2 hat is 1/3 times y1 plus 2/3 times y2. So in this case, the effective degrees of freedom for this model is equal to 2/3 plus 2/3. So this is actually the 4/3. So this is fractional. So in general, the degrees of freedom is between 1 and n, but maybe fractional. Effective degrees of freedom. Yeah. So basically, we have correspondence between lambda and the degrees of freedom. So lambda is equal to 0. The degrees of freedom. This is very flexible model. So degrees of freedom is n. Lambda is infinitely large, then degrees of freedom becomes 1. So this is the trivial model of yi hat is equal to y bar. So in between, then we have correspondence between lambda and the df. And we have, okay, maybe the lambda is equal to, I don't know, 0.1 or 1 or 10 or 100 and so on. Then we have the degrees of freedom. Degrees of freedom may be, like the 5.1 or the 8.3 or the 3.5 or so on. Okay, so we optimize lambda. So suppose the optimized lambda is 10, then we can determine the effective degrees of freedom is equal to 3.5. So effective degrees of freedom is fractional. Is it okay, or do you have some more questions?
No, thanks, Professor. It's okay.
Okay, so the degrees of freedom, number of parameters, that's integer, but this extended definition, yeah, so this the definition for the smoothing spline that can have fractional degrees of freedom. So actually the 6.8 degrees of freedom by LOCV. So that means probably if we fit the cubic spline, maybe we put maybe 4 knot points, 4 knots for cubic spline, maybe. Probably, because the 4 knots for cubic spline means the 4 plus 1 plus 1 plus 1 plus 1. Oh, sorry, maybe. So 3 knots, 3 knots. So 3 knots for the cubic spline, then the 4 plus 1 plus 1 plus 1, so 7. So, when we use smoothing spline, 6.8 is optimal. So that means if we use the cubic spline, probably 3 knot points is a good choice. Yeah, so it can also give the reasonable number of knots for cubic spline. Okay. Okay, so if you don't have a question, then we go to the next one. So this is a little different idea. So local regression. So local regression is non-parametric version of regression. So the idea is that we only use local information to determine the fitted value. So linear regression is global in the sense that we use all observations. So for example, suppose we have this data set. Okay, so probably this is not good to be fit by straight line, it looks. But suppose we fit the straight line. Maybe like this, right? But this is probably not a good line for at least these observations. Right, so probably the truth is probably like this kind of curve. But so the problem maybe come from the too simple model. But suppose we want to only use the straight line, but the problem can be interpreted as, okay, so these fitted values are affected too much by these observations. And these observations are far away from these points. So it does not really matter, right? So that is the idea of the local regression. So we use only limited information. If we use, for example, the first 5 observations to fit straight line, probably we can get more appropriate fitted value. So that is pretty natural idea. For example, we think about the side effects of some drugs by weight of patients. So if suppose that your brother or your son or daughter only have maybe 20 pounds, then probably you don't want to use the side effect data from the people with the 200-pound people or maybe 300-pound people. You want to gather the information of similar people, like the people with 25 pounds or 15 pounds. Then we take some average. So that makes more sense. Right? So, so local regression, the idea is this. So we use only limited information. So even if we only use very simple model such as straight line, it works well because we only use the the neighborhood information. Okay, so suppose we want to predict. We want to. Yeah, I think we don't have enough time, so maybe we start from this one next time.